Okay, so a couple key things. We were working on electric potential energy. We with the formula. I want to look at that again for a moment and then point out something kind of interesting. So we said that if we had a big old charge here of Q1, Anthony, and basically if we had another charge, like a test charge at of Q2 at infinity, it would take so much work to bring that test charge up this location over here, this location here, at distance r, from the Big Papa Q1. And we were looking for an expression for the potential energy at point P. That's what we did yesterday and the day before, for that matter. So another way of looking at it is that there's going to be increments of changing in the potential energy. You know, like when I move that sucker from here to there, you know, there's going to be a little change in potential energy, you know, right between those 2 points right there. And if I consider that little change in potential energy, whatchamacallit, that little infinitesimal change in potential energy would be equal to the little tiny bit of work it would take to move it between those 2 points. And that little tiny change in internal or potential energy would be equal to the amount of force it would take, S of A, times a little incremental distance, dr, right there. Work equals force times distance. And then, of course, if we integrate from 0 to the potential energy at P, du, and integrate over here from R equals infinity to R equals, I'll call it R sub P today. F sub A dot dr. Well, then, of course, we would get the total potential energy as P. If we add up all those little changes in potential energy, and we went on to say that, look, if you're pushing that sucker in with a, you know, certain amount of applied force, the electrical force is going to be in the opposite direction here. So it's going to be from R equals infinity to R equals R sub P of the negative of the electrical force by the electric field dot dr. And of course, we went through that. Potential energy of P is going to equal the integral from R equals infinity to R equals capital R sub P. But this term right here, we know that's going to be the Coulomb's law force, between the two charges. So that's going to equal negative K Q1 Q2 over R squared dr. And when we integrated this, what we end up getting K Q1 Q2 over R sub P. Been there, done that. Nothing new there. But what I wanted to point out, folks, was another little key thing that comes up that you need to be aware of. Let's just go back to this last slide right here. And it's this right here, look. Well, actually, let's, we can start right there. This here kind of gives us a little key to the relationship between the electric force and the electric potential energy. Electric force and electric potential energy. So let's start off with that and just explore where this takes us here. The little change in potential energy is equal to how much force someone's going to have to push that in times dr, but we know that that's equal to the negative of the electric force times dr. And notice, this tells us that the derivative of the potential energy function, dr, what does that end up telling us? The negative of the electric force.
Hola.
Good morning.
What's going on?
Nothing too much.
How come you hooked that way?
I'm recording this lesson.
Nice.
We're on live.
Where war? Well, that was interesting. I feel
I mean, this here is like the big news right here. And of course, you could write it the other way. You could say the electrical force is equal to the negative of the derivative of the potential energy. But we know that electric force is a vector quantity, and the potential energy function, of course, is a scalar. So this is in the direction of r. So you put in a unit vector right here, r. So let's look at a sample problem of this, because again, this is like a key relationship that you're going to have to memorize. The electric force is equal to the negative of the derivative of the potential energy function. So, well, actually, you know what? We're going to go on to this one first. Another key relationship is between the electric field and the electric potential. We talked about the electric potential from a point charge being equal to K Q1 over R. And again, we end up taking a derivative of this, and the derivative of the electric potential, R, of course, that's going to equal the derivative of K Q1 over R with respect to R. And of course, the K and the Q1 are constants. So that's the derivative with respect to R of 1 over R. And what's that derivative going to be? So we get negative K Q1 all over R squared. But what does that turn out to be? The negative of the electric field strength. So this is another key derivative that you need to be aware of. And basically, if we rewrite this here, we could say the electric field strength is equal to the negative of the derivative of the electric potential function. Now, once again, the electric field is a vector, so we have to put a unit vector in here as well. And of course, that direction is going to be perpendicular to the equal potential lines.
Is the negative necessary if you have the R hat? Or if you have the unit vector view, is the negative really necessary because it changes direction anyway? The unit vectors would choose the direction the negative is redundant. They're the same direction though, aren't they?
Well, I think the direction of that unit vector is from the higher potential. Actually, no, it'd have to be from the lower to the higher. That's a good question. I have to think about that.
Also, negative reduction.
Sure. All right, so let's look at a sample problem dealing with that. Here's a typical problem. given an electric potential function. E of x equals 5x squared minus 7x. Find the magnitude and direction of the electric field at x equals 3 meters. No, think about what we just said. We said that the electric field strength is equal to the derivative of the electric potential. We have to put a negative sign in there. And it's going to be in the derivative of x. So in this case, it's going to be in the derivative of the unit vector I. Take time, take a moment, do this problem with us. You do it in your head, great. If not, write it down. Alex?
23 Newton Coulomb towards negative x direction.
Right. So, but if you're using the unit vector I, which is the positive direction, you
So
take
negative 23 Newton Coulomb.
yeah. And a Newton per Coulomb is also a volt per meter. With that? Here you're looking at it though like with that derivative of the electric potential. So it's almost like a gradient of how much the electric potential is changing. So voltage per meter also kind of makes sense.
Now gradient is another mathematical term altogether. Come on.
You know when he gets back from that? He never just walked through his head.
And you see like in this problem here, like that negative sign comes in because the unit vector I is in the positive direction.
Is it in fact the gradient of the electric?
Okay, so moving on. So today we're going to be looking at finding the electric potential due to more complicated structures, not just point charges. For example, you have this charged ring right there. And the total charge of the whole ring is Q. And the charge is uniformly spread throughout the whole ring. And we want to find what's the total electric potential at that point P. Now, if you just had a little smidge of charge, we just considered the little charge, like let's say, you know, from here to here.
You like yellow today.
We're calling that delta Q. a little tiny piece of charge right there. Well, if we were going to find the electric potential due to that just little piece of charge right there, that delta Q right there, you know. And notice I don't have to put any vector arrow anymore because it's not a, you know, it's not a vector. Yeah, of course. We know that electric potential due to that little piece right there would be equal to what? What's the expression for the electric voltage? Yeah, well, that whole charge, that whole little piece is how far away from P? R sub I. So it would just be K times delta Q all over R sub I. That's not the voltage of the whole thing. You know, maybe I should call that the, you know, delta V. That's just the voltage due to that one little piece. But notice, all of the charge is that same distance, isn't it? Yeah. Yeah, we don't even have to integrate basically because, you know, the voltage there at that point P is going to equal K.
We're assuming that
Q.
Q, constant, right?
The charge is uniformly spread out all over R sub I. Because all of the charge is the same distance. But a lot of times it's not given in terms of R sub I. It's given in terms of like this distance here. From here to there would be like a distance Z along the Z axis. So what does this become? KQ over
B cos theta.
No. You want that R sub I. You don't want to bring in theta. You want to do it in terms of Z and capital R.
Oh. So then the square root of R squared. Square root of R
Yes.
squared plus B squared.
So V at that point P is equal to KQ all over square root R squared plus B squared. So that turned out to be relatively easy because all of the charge is located at the same distance, R sub I, from the point. So we didn't really have to do any fancy integrating. unfortunately, this next one's not going to be so simple. This time we have a uniformly charged disk, not a ring, uniformly charged disk of radius r. And again, the distance is z from the center right here. Yeah.
So we know what it is for a ring. Do we just integrate from 0 to r to get all the rings?
Exactly. Exactly. That's exactly what we're going to have to do. We'll do it piecemeal, ring by ring.
What do we know about electrical about this?
Yeah. Matter of fact, we should go back and check that out. Because we did a problem just like that where we found the electric field right there, yes? Remember?
Find the electric field from that.
And when we found the electric field there, what was the relationship between the two?
Gradients.
Also, v.
The electric field is just the negative, the derivative of the.
Can you just rewrite that also, though, if E is equal to VR?
If it's a uniform electric field.
Why only uniform?
You know, like if R was a constant, you know, E was constant throughout the whole R. If E is changing,
If then V is changing also in the same proportion.
Except in this case, we can't just apply dVdr because this is not a one-dimensional surface. This is a three-dimensional space right now. You need to use the gradient operator here. Partial derivatives for each direction, and then you get the right vector.
well, we're just going to consider it
It would be
a plane.
but it's not. This is three-dimensional. X, Y, Z. You wouldn't get the right thing.
So there's nothing that you have.
Yeah, you do.
We're going to get
That's where the point is. No, really.
the point P is along the z-axis.
You need to take you actually have to use the gradient operator. What? That's, yeah, but well, actually, that's while you do have that fact, you don't have, you can't just to make this the formula of that thing, the del v is negative del v is equal to E. It doesn't work that way. Yes, and because you think about it, if you move off center, you have different electric fields. You're talking about a derivative in 3 dimensions, which means it doesn't matter. It's not just the axis. What matters on the axis. You suddenly have vectors going in a direction if you go just off. All right. Think if you move that point P just off the z-axis to any direction. It's not just off the z-axis. No, but to find but for the to find the derivative of both potential, you need to have that's the change from in any direction. That's not change from one direction.
Let's just try to solve the problem here for the electric potential at point P. And we know how to do it for that ring there. And as Andrew said, we just have to sum up the effect of all those rings. So the little piece of voltage due to that little ring is going to be what? what is that going to be? K dq all over r sub I. Are you with me, people? The little piece of voltage, Andrew.
Yep.
The little electric potential just due to the ring dq is going to equal k dq over r sub I, correct?
Wait, wouldn't you want to put it in terms of dr, no?
Yeah, because wouldn't the R side be changing going over there?
Why are you putting in dq, not dr?
Well, at first we're gonna have to replace the dq, but dq is the amount of charge in that ring.
Oh yeah.
What about the dip?
What's that?
What about the dip? Not just the ring.
We're gonna do the sum of all the rings.
I get it, because I thought it was you were talking about little r, but it's r sub I, not little r. That's what.
I would integrate dq to the R.
They look similar, r sub I and little r. A lot of confusing variables. You have big R, little r, dr, and r sub I.
Yeah. So what can we say dq is equal to? If we use a surface area density,
So that's the signal for delta and the surface area?
yeah, that's the sigma.
Signal.
Actually,
Yeah, it's not surface area. I think it is most areas.
all right. Well, I guess we could use the linear density one then, right? Lambda. No. You have to use surface area one. So it would be sigma times the surface area of that little ring, but what's that going to be?
Yeah.
2 pi r times dr. You with me, people? And then we have the little tiny piece of the potential equals k sigma 2 pi r dr
All over the r sub I.
all over the r sub I. Thank you. Now, of course, that r sub I, we're going to have to make this substitution right here, right? And we're going to integrate that from 0 to r. So, integral of 0 to the total potential at P is going to equal from 0 to capital R. And what did we have? K sigma 2 pi. What was that?
RDR.
Oh, but which R is that?
So
Oh, that's little r, yeah. Like the regular R, not R sub I. So that's R, that's good.
and then over the square root of c squared plus r squared. Which is just dr. And then you have a tongue constant.
On the bottom, it's a capital R,
No.
isn't it?
No, it's lowercase r because it's a variable. It's going to change. It's going to change. You know, as you go, R sub I changes as you go to different rates because that R changes.
Oh, got it.
Where'd you get the sigma?
Well, we had to change the charge. So charge is equal to the surface area charge density times the amount of area right there. So if I was going to integrate that, I would do a U substitution. Is that how you guys would do it?
We've already done that in R10.
Yeah. You can just take it out and do R10.
So you can.
Yes.
If you have the R on top, the variable. Just pull up.
Oh yeah, you don't even have to worry about that.
If I was doing this, I would say
I don't even bother.
U is equal to Z squared plus R squared. So du
Yeah, I don't think we need
is going to
You don't
equal
need to do
to
that.
Okay,
2R
You have the derivative on top.
dr. And look, you got the 2R dr right on top. So that really works out as a nice U substitution.
You don't even need it. The anti-tunnel.
All right. So what do you get then? Tell me.
1/2 to integral 2r.
You'll need 1/2.
That's the point.
Keep the constant in there. Keep the 2 in there. Oh, yeah, that's constant.
No, because you have to do the interchange.
Yeah, you keep the 2 in there because 2 is constant. The derivative of r squared.
Whatever. So we keep the 2r in there.
Yeah, keep
keep
the 2 in there. Don't
Keep
pull
the
the 2
two.
out.
Keep the 2 inside.
Okay.
So you get equals k sigma pi equals r 2r.
And then it's just,
And then you get rid of the 2r because of the anti-tunnel.
yeah, so it's just 1/2. So you get 1/2 rise b squared plus r squared.
Yeah, 1/2. Yeah, 1. No, 2. Add 1 and then divide. So that's 2.
Oh,
2
2.
times b squared plus r
It's
squared.
2 times
Can we
square root of
use
b.
Yeah,
substitution
2
and
right.
not
Yeah,
divide?
use U substitution. I don't know your anti-chain rule. I would just use U substitution. I would have been done by now.
b squared plus r squared. And then you're done.
Yeah, it's just 2 times what's on the bottom there.
Yeah, 2
Yeah,
rad
but the U
b squared plus
substitution
r
is
Why
easier
does
to
it take
do.
you guys that long?
I don't know. My brain's not functioning.
All right, tell me what we're gonna have here.
It's just 2 times.
Take 1/2 there or no?
No.
Give us the 1/2.
We were wrong about that.
You don't need the 1/2.
Z squared plus R squared.
2.
It's rad Z
2
squared.
right here.
Yeah.
Yes, 2 rad
Square root
of z squared plus r squared.
I can't believe
And
you
then
guys
from
took that
0 to
long.
r.
My brain's not functioning this early.
Like that.
Yeah.
And from 0
From 0 to r. And then you
to
solve.
R.
Which is just r because 0.
Right.
Charlie.
But what is sigma equal?
You can use it.
Okay.
I don't know. It's in the.
Wait, q over a, right?
Yeah.
Okay.
So you just put that back in?
Sigma
The 2 pi on the top
is
cancels
the
out.
charge
Right.
for the whole surface area, which is what? Pi r
I r
squared.
squared, big R squared.
So we can put that in there. I'm going to finish this problem. It's the last thing I do. B equals
Then everything can.
equals K sigma, but for sigma, I'm putting in Q over pi r squared. Whoopsie. Times pi. Oh, you go wrong way. That's 2 radical r squared. So your final answer is B equals 2K capital Q over R squared times the square root of Z squared plus capital R squared.